And what I'm going to be doing is, over the next 40 minutes or so, is describing some of the work we've been undertaking, trying to model impulse control disorders, particularly gambling-related disorders that could be caused by dopamine medications that are used, as you all know, to treat Parkinson's disease. And so I'm going to be talking about a lot of data that we've collected with rats, because that is our area of expertise. So there's going to be quite a lot of graphs and even a bit of biochemistry, but I'll try and take you through it in a way that hopefully is going to make sense. And I'll try and keep an eye on the little chat window. So if there is something that I'm going through too quickly or that you'd like me to repeat, I will try and incorporate that into the presentation. This is my first webinar, so it's a warning. So hopefully we'll all just work through this together. So a bit about me and my research. So I'm based at the University of British Columbia. I've been on faculty here for nearly 10 years and started doing this kind of research through the support of Parkinson's Society Canada as a new investigator only about 3 years into my tenure here at UBC. And since then, we've gone on to look at other issues related to Parkinson's, including the use of deep brain stimulation in some of our models. And we've been really grateful to PSC because they've given us those little bits of funding that are so vital to get new areas of research off the ground. And then once you have that pilot data, you can then compete nationally and internationally for bigger grants. And so, yeah, without PSC, I don't think we'd have managed to make any of this happen. Anyway, without further ado, I have a single disclosure slide. So I have been recruited occasionally as a consultant for a couple of pharmaceutical companies, and I'm involved in some legal work recently. So what we're going to be talking about today, of course, is the fact that some medications that have been developed for use to treat the motor symptoms of Parkinson's disease can induce impulse control disorders, things like problem gambling, but also hypersexuality, compulsive shopping, hoarding, punding, and sometimes even an addiction-like profile to the medication that people are taking. And all of this is incredibly undesirable. And, you know, some of the people I work with perhaps don't realize the severity of some of these psychiatric disorders, but you read these case reports of people whose networks, supportive family networks, have survived, the low of a Parkinson's diagnosis, and everyone rallies around the patient and tries to help them through. But then when that patient develops particularly something like gambling disorder, which has pronounced financial consequences for the family and is stigmatized unfairly as being, maybe someone's fault, or they should have been able to do something about it. When people experience that as a result of their medication, that puts an added burden on all those support networks and all those family members and friends who've rallied around them. And that's really where, people experience extreme negative impacts on their quality of life. And it's really heartbreaking that a medication like these dopamine agonist therapies that are so successful in treating the motor symptoms of Parkinson's, and that's why they were developed, then had this unintended side effect in a minority of patients. And we're talking, conservative estimates put it around 20% of people who take dopamine agonist therapy, that they can develop these serious impulse control problems. And those sometimes can be worse than the Parkinson's diagnosis itself. So this has led some neurologists to be very hesitant to prescribe dopamine agonists, particularly the D2/3 agonists like pramipexole and ropinirole. You're leaving patients with fewer options, such as basically going back to L-DOPA again. And if L-DOPA works, and if you're not getting big dyskinesias as a result, then that's fantastic. But for some people, it really is a difficult medication for them to stay on. So what are we trying to do? So our questions, and what we hope to be able to contribute some knowledge on, is can we determine who is going to be affected by these dopamine agonist therapy-induced impulse control disorders, or DAT-ICDs? If we had an idea of who might be vulnerable, then we could potentially get a pre-screening, a cognitive pre-screening measure in place so that those people who are at risk of developing an impulse control disorder could be identified and maybe alternative medications proposed. One of our next questions is what causes DAT-ICDs? And obviously the medication itself would be like the primary cause, but we're thinking more, what is the neurobiological mechanism by which this medication leads to issues such as gambling disorder? And even though we know these medications are primarily dopamine agonists, that's their primary pharmacological mechanism, it wasn't obvious when these medications were developed that these drugs would lead to this big problem. That we don't really know why, what's happening at the level of the neurons that leads to these changes. And if we can understand maybe who might be affected and the cause, then we can work up to the big one, which would be, are they preventable? Is there something we can do either by filtering out those who may be at risk, or more ideally to develop maybe an adjunct medication that could be taken safely and effectively alongside these dopamine agonist therapies that would preserve their therapeutic use for the motor symptoms of Parkinson's, but prevent the development of these undesirable psychiatric side effects. So what I'm hoping to do is take you through some of the work we've been doing trying to address this using rats. The advantage of using an animal model is you have an incredible degree of experimental control over the history of that animal, you know exactly who his friends were, when he was born, what he's been doing in his life, right up until the time when you get him gambling and give him any Parkinsonian medications. So you can really try and tease out, is there a cognitive vulnerability that may make individuals more vulnerable to changes in behavior on these dopamine agonist medications. But before I get to the bit where we start giving them ropinirole, I'm just going to spend a bit of time talking to you about how we'd even go about modeling gambling behavior in rats in the first place. And some of you are probably thinking it sounds like a bit of a mad idea, but hopefully I'm going to convince you that this is something that we can do, and that there are steps that we can take to ensure that our models are robust and likely to develop or contribute to developments that are going to improve human health. I'm then going to talk about a couple of the rat gambling games that we've developed and what kind of things they measure and why we think they look like gambling. And then I'm going to take you through the data we've right, and so looking at the effects of these drugs on these animal models, what it is they do to the animals in terms of their behavioural changes, and then the potential drug target that we think we might have discovered. So when is gambling a problem? We all gamble a bit. Nearly everybody has had a flutter, whether it's buying a lottery ticket or just enjoying a night at the races or just a scratch card at a gas station. And there is very little harm for most of us associated with doing that. However, for some individuals, gambling becomes a maladaptive compulsion that shares significant overlap with a substance use disorder, or as it's commonly known, drug addiction. And the similarities between these two states, gambling compulsively and drug addiction, have led to the reclassification of pathological gambling, which is the impulse control disorder version that we used to be talking about here, instead to gambling disorder, which is now classified with addiction disorders in the latest edition of the Diagnostic and Statistical Manual that psychiatrists use to classify mental illness. So if we look at the symptoms of gambling disorder, it would sort of make sense that it be viewed as an addiction because the symptoms virtually overlap. They're very, very similar to drug addiction, only instead of talking about taking a drug as the maladaptive outcome, we're talking about engaging in gambling behavior. So key symptoms include tolerance to the amount that you gamble. So you start out getting enjoyment from maybe going just once a week and end up having to go multiple times and for gambling longer to get the same level of enjoyment. A negative state during withdrawal. When people try and stop gambling, they feel depressed and anxious, similar to how people feel when they try and stop taking addictive drugs. There are repeated unsuccessful attempts to quit. Again, very similar to drug addiction, where people find they are unable to stay clean, stay away from gambling opportunities, and of course a negative impact on the quality of life. Typically the huge financial losses, gambling away of savings, of college funds, and the loss of significant relationships as a result. People with gambling disorder also report craving, that strong urge and desire to gamble. There's a higher severity of gambling disorder with a younger age of onset, and I think it's perhaps notable that those with younger age of onset Parkinson's disease are more likely to experience impulse control disorders as a result of dopamine agonist medication. And there's also a phenomenon known as telescoping, which is something that affects females in particular, where women start gambling later in life, but the time period between their first initiation of gambling and the development of a problem is foreshortened, so it's telescoped. And again, that's very similar to what is seen with the drug addiction literature too. So these things look like they overlap quite a bit, and it's a significant mental health problem that we're trying to address. So if we're going to try and use animal models and benefit from all the experimental power and all the neurobiology we can learn from them, we have to take a moment to think about how those models are designed. So whenever you're looking at data from an animal model, particularly from the perspective of drug discovery, you want to know if that model is valid. And we have three tests. We have what we call face, construct, and predictive validity. So face validity is simply, does this behavior look like gambling? Does it superficially share some of the same features as the human cognitive process? Are these two different processes subject to similar biological regulation? So we can look at what happens, for example, in humans when an area of the brain is damaged. That implies a particular brain area is important for controlling gambling behavior. And then we can look and do the same kind of test in animals to see if selective brain damage likewise causes the same kind of change in behavior. And by doing a sort of a series of experiments like this, we can get a good approximation of, is it likely that the same brain chemicals and the same brain areas are controlling behavior in both the human and the animal? And that's an essential part of this validation. But the bit that we really want is what we call predictive validity. And this is, can you give a drug that you know is going to be beneficial in treating a human disorder, like schizophrenia, for example? If you give that drug in your animal model, do you see an improvement in behavior? And if so, then you can be reasonably confident that the same kinds of drugs that improve the rodent behavior are going to improve the human behavior. Now, unfortunately, we always have a bit of a problem with gambling disorder in this regard, because in order to truly validate your model, you need a drug that is known to treat gambling disorder that you can then give to your rats and show an improvement. And unfortunately, there is no FDA approved or other agency approved, universally sort of regarded therapeutic for gambling disorder. We just don't have a good cure for it in otherwise healthy individuals, never mind those with complications of Parkinson's. And so all our models are only, what we say, somewhat pseudo-validated. But interestingly, one of the things we have been able to do using our animal models is to look at the effects of drugs like pramipexole and ropinirole that can increase gambling disorder in human subjects and see if they do the same in the rats. So obviously there's many different types of gambling. So some people really enjoy going down to a racetrack, betting on the horses or engaging in other kind of sports betting. And that can be quite stimulating and exciting, and people feel a rush of enjoyment from doing those things. Conversely, things like slot machines or other kind of electronic gambling machines induce a very different kind of emotional and mental state, more like a decrease in stimulation and anxiety. People have talked about getting into the machine zone, finding this dissociative state where you just relax and forget about all other things and just become completely absorbed in the game. And obviously those two different kinds of gambling behavior involve very different kinds of cognitions. And most of the gambling that is induced by medications like ropinirole and pramipexole tends to focus on things like slot machines and scratch cards rather than the more intense thrill-seeking kind of gambling. And so that's something we've got to be aware of, that we're actually trying to model the behavioural processes that are most effective in humans. We can also talk about the motivation to gamble, like why is it that some people like doing this behaviour? What is it that they feel they get from it? And also cognitive biases. So this is a very interesting area of research that has really focused on what makes gambling disorder unique from other addiction disorders. And work in this regard has been really heavily influenced by folks like Luke Clark here up at UBC, who runs the Centre for Gambling Research, who's taken a psychosocial approach to this disorder and is looking at the psychological vulnerabilities to gambling problems. And it's been noted that people with gambling disorder tend not to think very rationally about uncertainty. So what do I mean by that? They're more likely to endorse things that are like superstitious thinking about feeling like if you wear your lucky pants that you're more likely to win on a particular day, to believe that they have more control over certain aspects of gambling games than they really do, and also to show changes in their interpretations of winning and losing outcomes. And I'll talk about what I mean by that in just a minute. So if we can try and model some of these processes in animals, then we could have a good chance at getting to a model of gambling disorder. So one of these decision-making biases is something that we all do to some extent, but seems particularly pronounced in folks who are vulnerable to gambling disorder. So what I'm showing here, let me get my pointer up. So this is what we call a value function, and in blue is the way in which we, as happy and healthy humans, actually value bets and gambles depending on the predicted losses and also the predicted gains. Now, the dotted line here in green, that would be what our decision making would look like if we were truly rational, sort of like a computer, making decisions based on mathematical theories. And the value of a potential gamble would decline linearly as the projected losses increase, and also linearly as the projected gains increase. But what Kahneman and Tversky found, who were two social psychologists who won the Nobel Prize for this work, is that human decision-making deviates from this green dotted line, and we all show this to some extent or another. We show this escalation of commitment bias. So as the potential gains increase, we actually start undervaluing bets. We become a bit mathematically irrational at this end. And what that translates into is if you're gambling for pennies, you're much more rational, you're much more willing to take a risk in accordance with the mathematical rules than if we're gambling with hundreds of dollars, in which case we become a lot more conservative in our gambling behavior, even if the odds are kept constant. Likewise, when we see this deviation down here away from the green line, this is known as risk aversion, and this just shows how incredibly unwilling we are to accept losses. Nobody likes losing, and we're actually willing to keep gambling to try and get away from those certain losses. But one of the simple tasks we've developed in rodents was just to see, do animals show anything like this kind of risk-averse profile as the amount at stake increases? And to do this, we had to figure out, of course, how to translate any kind of cognitive or behavioural task from humans into rats. And of course, we can't just use a computer, because despite rats being rodents, they're not very good with a mouse. Ha ha ha. Instead, what we use is one of these things called an operant chamber. So this is like a little Fisher-Price activity box, if you like, for rats, a place where they figure out that there's things they can do in this box that might result in delivery of these sugar pellets, which are these sugary treats, come down this little tube, and there's a food tray, a little area the animal can poke its nose to get that sugary treat on one side. And on this side, what you can hopefully just about see is there's an array of what we call nose poke apertures, or little response holes, and the animal can poke its nose into those holes in order to win or lose or earn sugary treats. And we program the rules of the game using a computer it's all wired up and attached on the outside. So that's where our animals are going to be doing their gambling. And so this is work done by my then graduate student, Paul Cocker, who set up what we call the rat betting task. And this is going to allow us to measure that sort of degree of irrational decision making. So this is our rat. Excuse my artistic abilities; they're not that fantastic. So the task starts. The start of each turn is when the rat makes a little nose poke response into that food tray to signal he's ready for a trial. And then 1, 2, or 3 lights are illuminated in those response holes, those nose poke apertures on the other side of the box. And what the animal has to do is just poke his nose in any order, just to turn off the lights that are at the back of that box. And the number of lights signals to the animal what the wager is, if you like, and that means how many sugar pellets are available on this safe lever. So 2 levers come out, one associated with a guaranteed reward and the other with an uncertain outcome. And the animal simply chooses what he'd like to do. So this rat, for example, if I can get him to move, say he chooses the safe option. There were 3 lights illuminated at the back, and that means he earns 3 sugar pellets. Now, alternatively, he could go for the uncertain option, and here he gets 50% of the reward available on that safe option, or nothing. So he's either going to get 6 sugar pellets or he's going to get 0. And the way we designed the task is that there is no net benefit to choosing safe or or uncertain. There's no real risk here. We're just looking at simple preferences for uncertainty. So do animals like receiving uncertain outcomes, or do they prefer to receive safer outcomes? And how does that change as the amount at stake increases? So we have different blocks of trials where the wager can be 1, 2, or 3 sugar pellets, and so they can earn those on the safe lever, or double that amount of reward, or nothing on the uncertain option. Again, we were hoping to find some animals at least that would show a nice escalation of commitment bias and back away from that uncertain option as the amount at stake increased. And that's exactly what we found. So I'll just orient you to how these graphs are going to work. So here on the y-axis, you have the percent choice of the uncertain option. So how much time are animals spending choosing from the uncertain lever? And here we have the amount of sugar at stake, 1, 2, or 3 sugar pellets on the safe option. And what we find is that animals show sort of 2 profiles of behaviour, if you like. They're either pretty insensitive to the bet size, which means they're kind of mathematically rational. They figure out how much they like the uncertain option versus the safe one, and they're not really fussed by the bet size. They just prefer it regardless, which is mathematically what they should do, if you like. However, other animals show this really marked wager-sensitive bias, which looks much more like the escalation of commitment that many of us show in our human decision-making, which is that when there's not very much at stake, we prefer uncertainty much more than when the bet size increases. And animals vary quite a bit, so this sort of gives you the gradient of that line. So if it's a very steep line, that shows the animal's highly wager sensitive. If the gradient of that is very negative. And so you have animals that are either highly wager sensitive or that are pretty mathematically rational. And so what we wanted to do was have a look at the neurobiology underlying this decision-making bias. We were quite excited to find that it does exist in rats, so that we can look at some of these hallmarks of choice under uncertainty using animal models. One of the first things we noticed is that decision-making, or the degree to which animals show this wager sensitivity, seems to be strongly related to the level of dopamine D2 receptor density in an area of the brain called the dorsal striatum. So again, we know that D2 receptors are the primary pharmacological target, the primary way in which dopamine agonist medications influence motor outcome, and also we think may well be causing these psychiatric side effects, these impulse control disorders. So it was interesting to us to see that the density of D2 receptors predicts how wager sensitive animals are. So the greater the D2 receptor availability here, actually, the lower the wager sensitivity. So we did this experiment using a PET scan, and I don't know how many of you have had PET scans to look at dopamine function as part of either a research study or maybe as part of a monitoring of your disease, but we can do exactly the same thing with rats. Put them in it's a much smaller machine, a little PET scanner, and give them a radioactive tracer, and that shows how many dopamine receptors are present in the animal's brain. So this behavior looks like it may be affected or impacted by dopamine D2 receptor activity. So this is work done by Melanie Tremblay, who's another excellent graduate student of mine. And what we did here was we gave a dopamine agonist medication, ropinirole, and we gave it chronically over 28 days. So this mimics more the way in which this drug is used clinically, rather than just giving injections. We developed the equivalent of a slow-release formulation. So we used something called an osmotic mini pump, and that's basically just a little pod filled with concentrated drug that we then insert just under the animal's skin. And over time, the construction of that pod is designed so a certain amount of drug will slowly leach out constantly, thereby treating the animal with the compound. And what we found before we gave animals any drug, of course, we can nicely match their behavior. So we know before the animals take any ropinirole or are given any ropinirole that their decision making is the same. And here's what happens when we have animals taking ropinirole. Again, this is the degree to which animals are choosing the uncertain option. And I hope you can see this is a really big jump. So suddenly our animals who are taking ropinirole, after 4 weeks, they're showing a really big bias towards uncertain outcomes. And then when we take the ropinirole away and put the animals into withdrawal, this completely disappears. So it looks like that's sort of the equivalent of doing a baseline challenge and de-challenge investigation clinically. You give drug and then take it away and see if the behavior normalizes. Now, one thing we were interested in, of course, was seeing whether there would be anything in the animal's behavior that might predict whether they'd be more likely to be affected by the compound or not. And so we looked at the degree to which animals showed that wager-sensitive choice bias, the degree to which their decision-making varied as a function of the amount of sugar at stake. And Melanie went back through each individual animal to see if they showed any significant change in their own behavior individually when given ropinirole. And we found that certainly there were animals that were more vulnerable to the decision-making change caused by ropinirole than others. So here we call these animals responders, and the animals that didn't show a significant change, we called them non-responders. But we see responders and non-responders both in animals that start out as pretty wager insensitive, they're quite mathematically rational, and also in animals that start out being very wager sensitive, less mathematically rational. So it doesn't seem to matter whether these animals have a bias towards uncertain outcomes or a bias towards thinking irrationally about uncertain outcomes to begin with. What happens when you give them the drug is that about 2/3 of them show that increase in choice of the uncertain option, and it doesn't matter what their baseline behavior is. So these data would suggest that there isn't a sort of a pre-drug cognitive state that may make it more or less likely for someone or an individual to show a gambling problem after ropinirole. It's simply a function of the drug itself and whether you have maybe a neurobiological vulnerability to that compound. But there's nothing cognitively that's predisposing subjects. Now, it's great to see that was in otherwise healthy animals, but what we want to do, because it's relevant to Parkinson's, is look in an animal model of Parkinson's disease. And so this is what the sort of histology or the brain slices look like from animals treated with a compound called 6-hydroxydopamine that selectively destroys dopamine neurons in an area of the brain that you target. So here we're going to target a motor area of the brain. This is the striatum. And in rats, it takes up a lot of space in the animal's brain. We all have a striatum too, only it's a bit smaller relative to the size of our cortex. And this staining here, this nice dark brown, that's all neurons that contain dopamine. And hopefully you can see there's like a bare patch here. And this is where we've put this special compound in that destroys the dopamine neurons. And that just shows all this close up. So there's an area where we've taken the dopamine neurons away. And so we can use this to approximate early onset Parkinson's disease. And we do this bilaterally. So it's on both sides of the animal's brain. It does lead to a mild motor impairment. So we look at the number of steps that the animals are taking in a sort of stepping assay, and we do get a mild impairment in animals that have a lesion to their dopamine system. And importantly, when we plant that little pod, which contains the ropinirole, the mini pump under the animal's skin, we can get a restoration of stepping levels back to the same as controls. So here's our sham operated animals that don't have dopamine depletion, given ropinirole and saline. Here's our animals with a dopamine lesion showing lower levels of motor activity, but ropinirole can restore this. And so it's nice also to make sure we include that kind of validation in our model, because if we do discover, and I'm hopeful that we will, a compound that might reverse the psychiatric side effects of ropinirole, we're always going to want to make sure that we don't also reverse the motor benefits, because that wouldn't be very useful clinically. So when we look at our animal model of Parkinson's, again, we're going to give ropinirole, this drug that induces dopamine agonist induced gambling disorder, or can do at least. Does it matter whether or not the animals are Parkinsonian or not? And certainly our data and data from another group would suggest that it doesn't. So we still get an increase in choice of the uncertain outcome when we give these animals ropinirole. We have animals that show a response, animals that don't show a response to drug. Here are non-responders, here are responders. And the animals that have the 6-hydroxydopamine lesion, the Parkinsonism, their behavior looks exactly the same as those that don't have that lesion. So again, what this tells us is that it's not something about the Parkinson's that may be causing this adverse drug reaction. It's something about the drug itself. It's the medication more than the disease state. And again, this is hopefully going to give us clues as to how we can reverse it. So we're talking a bit about how does dopamine change behavior and brain function. And as pharmacologists, we really focus on that brain chemical dopamine binding to a receptor, in this case the D2 receptor. And then that's as far as pharmacology goes. But really, once those molecules bind together, that triggers a whole host of changes inside the neuron that actually result in behavioral change. So these are called intracellular signaling pathways. And you can think of them sort of as what happens when you start a line of dominoes going. So this first domino here would be sort of the dopamine binding to the D2 receptor, kind of like putting a key in a lock and turning it. And by turning it, you then trigger all these other changes too, this whole array of things that happens that ultimately results in something happening to the neuron. Now, it was thought for the longest time that when dopamine bound to a D2 receptor, there was just one line of dominoes, if you like, that could be implicated. And this is just a biochemical signaling pathway. So all these abbreviations just stand for different chemicals, different proteins that are activated or not activated. And that little P there, that stands for phosphorylation. And that's just basically whether a certain protein is in an active or inactive state. Now, I'm sure many of you are not going to be super keen on the idea of a quiz on biochemistry at the end of this. But the point that I just want to make is that recently, just a few years ago, it was discovered there was a whole nother pathway by which dopamine binding at D2 receptors could influence activity using all these other different kinds of proteins, culminating in something called GSK3 beta, which has been a therapeutic target for a number of diseases, and we didn't realize that it could be influenced by dopamine signaling via D2 receptors. So now, rather than just one pathway that dopamine could be activating, and changing neuronal function for, there could be at least another one, and maybe even multiple other pathways that we weren't aware of. So one of the things we were wondering is, in our responders to ropinirole, do we see any evidence that one pathway over the other might be impacted if we look at the brains of those rats? And because they're rats, that's what we're able to do. So this is using a molecular biology technique called Western blotting, where you simply look at the level of different proteins that are expressed in the brain. And we looked again at this motor area, the dorsal striatum, which is an area that we know is implicated in this kind of decision making. And what we saw, first of all, is that we've got our animals treated with saline, we have animals treated with ropinirole that didn't respond by an increase in uncertainty, and animals that did. And we can see in our responders that there seemed to be lots more of the dopamine D2 receptor present, and we don't know if that's an upregulation that was caused by drug treatment, or if that was something that was there before we started giving the animals drug, of course, but it's certainly an interesting observation. But we also saw an increase in this GSK3 beta protein that was just selectively significant in animals that responded for drug and not in animals that didn't. In fact, animals that didn't respond for drug actually showed decreases in a couple of these other proteins that would suggest that in those, that original signaling pathway is being activated, whereas in responder animals, we're getting a totally different kind of signaling pathway activated by the same medication. Now, it's always good to see nice, robust findings in one experimental paradigm, but what you really want to see is the same kind of behavioural change caused by the same compounds over multiple behavioural paradigms, and that gives you more confidence that your findings might be real. So I'm going to switch gears a bit and talk about another kind of gambling game that we've developed in rats that was designed to, again, tap into one of these other cognitive biases that we see in people with problem gambling, and also that we're all somewhat vulnerable to, and that is the near-miss effect. So a near miss is when you feel like you nearly won, like you almost got there, and they're particularly prevalent in slot machines and electronic gambling machines. So in a slot machine, a near miss would be when two of the stimuli line up and the third one just misses. And so you feel when you see those two stimuli that you're getting closer and that you might be able to win next time. And there's been a lot of research on the biological, the neurobiological basis of this effect done with human subjects in imaging paradigms. And it seems as if these near misses, they make people want to gamble more often, even though they find them very frustrating. And so we wanted to see if our animals were sensitive to near misses and whether they could play a slot machine type game. And the way we do this, again, we're going to use our 5-hole boxes. Here are our array of 5 holes. And again, this is work done by my graduate student, Paul Cocker, as part of his PhD. So the task's going to start, the animal's literally going to hit a lever, which is sort of like cranking that old slot machine lever to get the wheel spinning. And that's going to start one of the lights flashing at the back of the box. Unfortunately, I'm not sure the flash animation is working very well. So imagine that light's flashing away, and the animal pokes its nose in that hole, and that starts this other light flashing. And so he's then got to poke his nose in that hole, and when he does so, that light stops flashing. And again, that starts the third one. And when they make a nose poke response, that's when the lights are set to off or on. Now, depending on that light pattern, there is either going to be sugar pellets available, so the animal might have won, or he's going to lose. Now, this is a classic win. So all 3 lights are set to on, and so the right thing for the animal to do here is to try and cash out. So if he hits the collect lever, he earns 10 sugar pellets. However, if any of those lights set to off, so this would be more of the classic near miss, where the first 2 lights set to on, but then the third one, when he nose pokes, it's set to off. Now the best thing for him to do is just roll again, because there's no sugar available on this kind of trial. And if he tries to collect, then he's subject to a 10-second timeout period. Now he's got 30 minutes to try and maximize his sugar pellet profits on this game. And so these timeout periods sort of eat into the amount of sugar that he can ultimately earn. So originally what we wanted to see is, can animals even do this kind of game, and what does their decision making look like based on the number of lights that are available. So if the animals are super smart and not sensitive to any of these near miss like stimuli, they should only hit the collect lever on full win trials up the top here. But what we're going to see is they actually show a bit more of a complex pattern than that. So this is what decision making typically looks like. Now on the y-axis now we have the percentage of trials on which they try and cash out. So when they think reward is available, based on the number of lights that are illuminated in that sort of response array. And typically what we see is that animals are really good at telling when they've won, when all 3 lights are on, and they're pretty good at telling when they've definitely lost, when none of those lights set on. And there's a small increase in the errors when there's only 1 light illuminated, but something we've seen time and time again is that error rates are disproportionately high when you get 2 winning stimuli out of 3 turned on in that array. And they can be up as high as 80 or 90% in some animals. And despite literally over 100 training sessions, we cannot get rid of this systematic bias. And we don't think it's that the animals can't tell the difference between 2 lights being on and 3, because there tends to be subtle variations in response rates based on the exact spatial location of these values. And we also did a number of control experiments where we just looked at discrimination, like can the animals tell in a much simpler task that 3 lights is different from 2? And they definitely can, but there's something about presenting those 2 light trials in the context of this slot machine-like game that makes them think they're more likely to have won when those lights are illuminated. And so from that perspective, it looks a bit like a near-miss effect. So what happens when we give animals performing this kind of game? What happens when we give them ropinirole in exactly the same way? So we did this over 28 days, and initially we did start seeing some changes in decision making. So again, you can imagine this is sort of an index of how likely the animal thinks there is for them to have won. And again, they're really good on win trials. They're pretty good on straight loss trials. But when they're taking ropinirole, they are more likely to think that they've won on loss trials. So that's the difference between those 2 lines. But that doesn't last. So within sort of 3 sessions, they've sort of gotten over that bias, and they go back to their previous drug-free choice patterns. And if anything, after 28 days, they're almost better at telling when they've lost than when they've won. There doesn't seem to be a big change in decision-making caused by chronic ropinirole, at least in this model of gambling behaviour. But one thing that is really hard to not notice is just how much more engaged animals are, how much more motivated they are to perform this game. So we look at the number of trials that they do in every session. So this is now along the y-axis here. And so this would be, how many turns do they have? How many times are they willing to hit that roll lever and get the lights flashing? And this is the number of sessions that they have where that ropinirole mini pump is implanted along here. And what I hope you can see is that the ropinirole treated animals are making way more trials, completing way more trials than animals treated with saline. And we tried to see if we could reduce sort of task engagement, if you like, by removing win trials. So the animals were playing, but they never won. And instantly you can see saline-treated guys really reduce their motivation to play this game. And ropinirole-treated animals eventually drop off too, but the slope of that line is much more gradual. And again, in the first session where they don't have any win trials, it didn't even seem to make any difference. They just kept playing as much as they ever had. And as soon as we put win trials back in a sort of reinstatement-like paradigm, again, our ropinirole-treated guys showed really rapid reuptake of their willingness to play that game, and we could never get levels of task engagement to be as low in our ropinirole treated animals as they were in our saline treated animals. So again, we can look at the animal's brain after they've been taking ropinirole, and we can look immediately after the last session in which drug was on board, and then we can remove the drug and see if behavior normalizes, and then look at some of those animals. And that gives us an idea of, maybe what changes in protein could be causing the behavioral effect versus just inadvertent or unrelated. So we know that when we take the ropinirole away, that the animal's behaviour goes back to pre-drug levels. So that increase in trials completed, that increase in task motivation goes back down. And so we want to look for changes in protein expression that are particularly prevalent at this point when the drug's still on board and maybe absent here. And again, we looked like we saw an increase in levels of dopamine D2 receptor that were present immediately after ropinirole was on board, but then weren't present afterwards. We also saw changes in dopamine D1 receptor expression that we're following up, and this was different from the previous study. And again, we seem to be seeing very long-lasting changes in levels or other activation here of this GSK3 beta. So here, phosphorylation, it's something that can happen to a protein. And in this protein, when it's phosphorylated, it's inhibited. So its behaviors or any of its actions are reduced. But following ropinirole, and looks like for quite a long time after ropinirole, we saw really low levels of inhibition of that protein. And that sort of lines up with the first study, also pointing to the fact that this protein could be implicated in some of the effects, potentially, of ropinirole on gambling behavior. And implies that there could be this other signaling pathway, again, implicated following activation of the D2 receptor. So what I hope I've shown you is that rats can perform gambling-like games that look like the behavior looks superficially like gambling. These behaviors are sensitive to ropinirole. We've reproduced each of these changes, the increase in trials completed on the slot machine task and the increase in preference for uncertainty on the betting task. We've now seen this in both of them in two totally independent replications using different rats. The first effect we've actually repeated about 4 times. And so we're confident this is robust, this is reproducible behavior, and that we can actually now try and target reversing of that behavior with any new drug lead. So at the moment we're chasing our GSK3 beta finding. We're also in contact with a couple of very, very small pharmaceutical companies who might have some interesting ligands that they want us to test out. So we're going to see if either of those might be any good. But one thing I think that is clear from our data, and is also clear from others, is that it's not obvious based on sort of the gambling behavior pre-drug which animals are going to show the biggest response to ropinirole. And I think, and I hope that's kind of a good message to get out, that if anyone who's experiencing these impulse control disorders, there's been some debate in the field as to whether all this does is just sort of unmasking some latent tendency that was always there. And our data suggests that's not the case, that it's simply a response to the drug. There's nothing within these animals or within, these patients that could have predicted whether or not they show this behavioral change, at least in as much as we can tell from their cognitive behavior. So maybe there's a genotype, maybe there's something genetically, or there's something different maybe about the way their dopamine receptors work. But it's not that these individuals had some latent impulse control problem that's then unmasked. It's purely the effect, we believe, of the drug and not of the disease and not of the person. And hopefully, using these kind of models, in a year or so, I'm going to be able to come back and give a webinar on the great strides we've made in terms of trying to find pharmaceutical compounds that can be safely and effectively given in conjunction with ropinirole and pramipexole that will reverse these unwanted side effects but don't impact their ability to treat motor symptoms. So that's all I have for you today, and I just need to thank all the wonderful